There we go. So go ahead and take a couple minutes. We'll do both of these warm-ups and then we'll talk about some stuff. I think there's a disconnect right now in what people are focusing on right now and between what what the big picture is. So I want to refocus or, give another example of that.
Oh yeah, it was just right here. For whatever reason, yeah. Only Excel is the whatever the operations that they use. Excel seems to understand what's going on.
Yeah, like we can only call mine Excel. Some issues as well.
Oh really?
Yeah.
Yeah, no, I got more fine with just using Excel for cheap. What other issues giving you?
No, it's just online Excel and Excel. Well, I'm not working out, but yeah.
Yeah, Tracy should put like a disclaimer, like don't use sheets or
Yeah.
anything else.
Change the order of these. That up there so we can work on this top one first. It should be fairly straightforward, this one. Remember, if you need to, you can separate this into two. That does not show up very well. That green sucks. Is red better? These are dry erase markers. Suck ass. They're big too. They should have been good. Is that visible?
It kind of hurts your eyes to look at it. Or that you think.
No.
I start all the time.
It doesn't like so hold up, but that might make it.
Neon.
Blue's a little better.
It's like white. That's like
That's
writing.
orange.
That's a lot better.
How's that, guys?
Yeah, it's way better.
I think that's the slow way of doing it. I wouldn't do it like that, but it is important to, if you're struggling with what it means, you could write it out like that. I think that's not useful. Although that's because these vectors, these things have something in common. Well, I could just do it as is. And then what's the interval of cosine?
Sine. Well, actually, look quick.
And what happens with that 2t?
So 1/2. 1/2. Got it.
It becomes a 1/2, right? What about sine of 2t?
Oh, yeah.
Negative 1/2 cosine 2t.
And we're evaluating from 0 to pi over 2. So if I do pi over 2, what's my first factor?
Zero.
Plugging pi over 2, sine of 2 times pi over 2 would be sine of pi. Pi is 0. Sine of pi is 0. And we do it on cosine 2t, 2 times pi over 2 is pi. Cosine of pi is -1. -1 times -1/2 is +1/2. Because that's -1/2 cosine of pi. Now we plug in 0, the math is kind of easy. 2 times it doesn't change it. So sine is 0 and cosine is positive there. Positive 1 times negative 1/2 is negative 1/2. And if we add those vectors together, what do we, or subtract the vector? It becomes 0, 1.
What if you do a U sub for 2t?
I couldn't hear that very well. What?
That's where you get the 1/2.
That's where you get the one.
Yeah, they're asking what would happen. What do you do? Like what happens if you sub the 2t? But that's, I was just saying that's where you get the 1/2.
Yeah, that's where the 1/2 comes. If you need to do U sub to do the 2t to get the 1/2, please do. So that's it. We start with a vector, we end up with a vector. Let's take a look at the other one, because on the other one, we do not have a vector. So take a gander at that one. Make sure everybody's on the same page. What's the first step here? Can I integrate that as is?
Yeah.
No. We cannot integrate that as is. This says do the norm. We got to write this in norm form. So we're not integrating those things separately. Sebastian's on Zoom today. What?
Jeez, calling him out.
He's normally in class. I hope you're feeling all right, Sebastian.
Yeah, I'm
Probably
doing
woke up
fine.
late. You
Yeah,
woke up
thanks.
late, didn't you?
No comment.
Question like this, going half it, so you got a question like this one, say you edge line. You can just kind of start all over. Possible.
Someone help me solve this. What should I do? What's a good choice here?
Take the t out and 1 plus t squared, enter the square root, then do a use up for
So when you say
Square.
take the t out, we're factoring out a t squared, then we can pull that out, right?
Yeah.
And then I heard a use sub. What am I doing a use sub on?
doing use up t squared plus 1.
I like that. Does anyone else agree with it, Eric?
No, James doesn't.
Seems like a good choice, right? U equals t squared plus 1. What do I do with u?
Du equal 2t dt.
And what can I do with that?
Take the 2 on the other side. Then
You can pull the.
So we got the t, the dt right here. I can swap it out for the 1/2 du. I'll put the 1/2 on the outside. And now I've got square root of u du. What are my limits of integration?
u0 is 1, u2 is 5.
How'd you get that?
Plug in t squared plus 1 for 0 and 2.
So you evaluated these in here, okay? Now what?
Integrate it.
What's the integral of square root of u?
That's
2/3 3 to 3/2. Okay.
yeah. Yes, yeah.
Does everyone agree with that?
Yes.
And you get that by rewriting square root of u as u to the 1/2 and going from there. All right, so the 1/2, the 2/3, this is just 1/3 out front, and we are doing 5 to the 3/2 minus 1 to the 3/2.
We don't know.
5 to the 3/2 is 5√5. And 1 to the 3/2 is just 1. And can I simplify that?
I can't think of one to simplify. Is there a way to simplify it?
If anyone knows of a way to simplify that, please enlighten me, because I'm not. I don't know how to do that.
I would keep it as is.
That's an
Okay.
exact answer. Anything you do in a calculator that converts that to a decimal is an approximation, and you don't want to do approximations. Decimals are bad when you're working for doing exact shit. Anyone need that up longer? Just say so now, or I'm moving it. Okay.
You should have said something if you still needed it.
Yeah, it's Lawrence, right?
What?
You're the one that waited for me to move it and then wanted it longer.
No, he's writing it. He's still writing.
Wasn't me. My hand looked like.
You're right. You're right. It wasn't James. It was definitely Lawrence. Wait, I said that backwards and died.
All right, so where is this disconnect happening with students right now? This is what's going on. I was repeatedly asked by good students, since they got A's on the first test, what's going on? What is this vector shit doing? Where is it? Where are we at here? So I thought let's just look at it in 2 dimensions real quick, what we're doing. I want you to not think about vectors for a second. Let's go back to what we did in calculus. So if we had some curve like this, and I wanted to find the tangent vector or the tangent line at, say, x naught right here. We would take the derivative and find the value right there, right? And the tangent line, the tangent or the derivative gives us the slope of that tangent line. And then, so the derivative of, if this is y or f of x, f prime of x gives us the slope of the tangent line, m tangent. And then what we would do with that to find this actual line, if we wanted the actual line, is take that and do something with y equals mx plus b, where we use the x value at that location. So we have y naught equals m times x naught plus b to find our b value. Once we find the b value, we have the equation of our tangent line here. That's what we did before. That should all be a recap. Well, that's what you guys did before. We haven't done that in this class. So how does that connect with what we're doing now? So where we're going with this is it's handy to look at what is happening to something that is on a curve like this. Picture this as a mountain road, and you're driving. Mountain road is a great one. You're a car on the mountain road. Put some wheels on it. Zoom. That does not look like a car. That's a terrible car.
Looks like a Hot Wheels.
There we go. So we're driving along this mountain road. This is a curvy road. And when you're in the car, you feel shit. Like if we're going around a sharp curve, we feel forward acceleration, but we're actually moving inward. So we're heading to, like, we're curving this way. The direction we're actually traveling is that way. We have a component like this. What we're doing, and this is changing all the time. Like if your experience for it is always centered to where you're at. So like on a curve, when we're turning left, we feel like our body is pushed to the right because we still have forward motion in that direction. And so that's to the right of the path we're going. So it feels like we're being pulled to the right when we're actually turning left. So like staying in this constant frame of reference here is kind of hard to do with the unit system that we're using, X and Y. So what we're going to do is if you will find as we shift and go down this rabbit hole of vectors, if we treat this as a position vector of R of t, we can pick some initial t naught. Let's say t equals 0 here. And so that would be R of 0. And then I could have R of 1, t equals 1 here. But from the car's point of view, does this vector mean a goddamn thing?
No.
No. You're driving along in the car, going down the road, the vector means nothing. The vector means nothing here. It is a position vector. So R of t is a position vector. It gives us a position where we're at if we have a coordinate system. It makes it so when we shift to doing, looking at stuff from the position perspective of the car, it's a little bit easier. So we don't actually need it. Don't fixate on this vector here. Now, our prime, by using it, we can get this vector right here, which is kind of useful. by shifting to the position vector thing or using R of t, calculating R prime of t at whatever time this is, t naught, we'll say, well, I'll say TA. So this would be R of A. Calculating this gives us, from our car's perspective, R prime is a velocity. It's a velocity vector. It gives us our forward direction. So we'll call it V. V by itself, that looks like a triangle. Let's move that V down a little bit. That's just giving me this vector right here. The vector doesn't have, it's not related to the coordinate system right now. That same vector I could write right here. So if I want to talk about the tangent line there, I have to, like, this is V also. This is V. That's V. To relate it to this vector right here, I need to call this, I need to say this is R naught, or R of A, not A, not a zero, but R of A plus V. And so V here is R prime at T of A. That's my tangent line, or tangent vector. Tangent line, I should say, tangent line. Why am I trying to write it in this little thing? I don't need this part anymore. R of A was to illustrate where we're doing it. This is the tangent line. Which is basically, it gets me to here. This is R, the position of RA. It's telling me where to start. It's a point, and it's giving me a direction from there. So that's my forward direction. I'm on a curve though. So I have some acceleration going, and we're going inward. We're not going a straight line. There is some form of acceleration going this direction. R double prime is going to be pointed in this direction. And since I'm doing this at time TA, that's R double prime TA, R double prime is an acceleration vector. So we will, when we get into 12.5 or 12.4 and 12.5, this is a normal vector. We call this vector here N, capital N, and we can do it as either a function of time, or we can do it as a function of arc length. And we can do the same thing here with R. I'll just leave it in terms of time for right now, because that's what we're talking about. So that's my normal vector there. We will see, since you're interested in where this is going, when we do in 12.6, where we're actually putting this into physical stuff and not just talking about the mathematics of it, we can see that the car is actually going that direction. So we will break down this acceleration vector into components that are related to the acceleration in the normal direction and acceleration in the tangential direction. And that will help us make this vector here. And there's some things that we can, I need to get rid of that right there.
So basically, it's centripetal force and tangent.
Effectively, yeah. So when we're doing 12.6, we'll break down this information. But right now, we're just learning the math of what the hell these vectors are. So the first derivative is a forward direction velocity vector at a given point. If I'm at a different point, if my car is way the hell back here, we got something completely different going on. So my position is very much, well, now I look like a fucking tank. My tangential vector here is that way. but I'm going down a curve. My acceleration is this way. That would be my A, and this would be my B. We will see that the normal vector always points inward along a curve. The tangential vector is a straight line from the point, the way the forward direction would be going. And so this is acceleration vector. We can call that A. But again, the R vector is just a position vector. We could just have, I'll do it as a dotted line. R of t at any just given time is giving us our position along this road. And we can use its derivatives to find out the velocity at that point and its acceleration at that point. We've got two vectors. If we're in three-dimensional space, we are going to have a third vector that points straight out. Boom, straight out at the camera right now. That straight out vector, the third vector, I got shit in the way of the camera. The third vector is called the binormal vector. And unfortunately, I don't know, I wish they didn't call it the binormal vector, because then they feel compelled to use the letter B like this. But what does this mean to anybody else that's taking physics?
Isn't the third derivative also defined as jerk?
Jerk.
We haven't done the third, there's no third derivative. I didn't do the third derivative here.
Oh, okay.
This is I didn't mean third derivative, I meant third vector. It is not R triple prime.
That's supposed to mean something to us. I don't think we've ever used that in physics.
B is T cross, B in physics is the magnetic field.
Oh, what?
Are you guys were doing
Okay.
electricity already?
Electric
field.
So in physics, it's the
Yeah,
magnetic field, B is. So I wish they didn't use B here for the binormal vector, because it's not the same thing. There's nothing magnetic about what I'm talking about. So we will ignore the magnetic, just separate that when you're doing physics or magnetism, keep that in mind. And we can calculate with T cross N, and we will, that's where we're going. This is what 12.4 is kind of on, but like, and we're going into what's happening at a given point along a curve for something on that curve. We're making physics that relate to real life. So that's where we're going. And that's, and using the R vector and its derivatives gives us a really great way of doing it. But R of t has nothing to do with the road that we're traveling on. So don't fixate on the position vector. It just gives us our location. What? Is there any questions?
No, although I wasn't expecting to learn more physics in this class than I did in my actual physics class.
You really just learn the basic.
I mean, in physics, you guys have, if you've taken physics 55, the kinematics, if X is your position, dx dt is your velocity,
Yeah,
and your acceleration is the second derivative, which is dv dt.
yeah.
This is the vector version of that. And it allows us to figure out shit of what is going on directly from the point of the view of something that's on that thing.
Yeah. That's actually pretty interesting.
I have a question.
Yeah, I got a question over here.
If can we go up and so we can see the graph? Is there an acceleration tangent on the velocity vector? Like we
Okay, so our actual acceleration ends up being like, which direction is the car going? The car is going this direction. So, because we're curving, so we break down the acceleration vector. This is the N of t is the acceleration vector. We're going to break that down in 12.6 into components that are this way. We call that acceleration in the normal direction. And in the tangential direction, we call it acceleration in the tangential. That is a really fucking hard word to say. Tangential.
Tangential acceleration.
It just is awkward. It's in the same direction as the velocity vector, the tangential acceleration. And then our overall acceleration ends up being in this way. But we'll see that coming up. My big deal is right now is we're not there yet. I'm just trying to give you, like, you want to know what the hell we're doing it, why we're doing it. This is why we're doing it. We want to have a frame of reference from you, and you're the little dude. Oh, let's make you Donald Trump. We'll use an orange person. Oh, that doesn't show up very well. Orange
I mean,
sucks.
It's relevant to kind of the chase button on there. It's like that's hiding the document.
You got a big
If
head.
you want to news.
So you're in the car. What is going on for you? That's what we're working on. So big, that's our big picture. At least in terms of physics.
That's what it's.
But we need to learn the mathematics to do all this. So that's why we're just focusing on, we're not talking about it as in terms of acceleration or velocity. We're just talking about it in terms of the tangent vector and the normal vector for right now.
Do you happen to have the textbook handy?
I do have a textbook handy, yes.
I was wondering if you could go over 45 on 12.2.
That's funny. That is fucking fantastic because I was going to do that. I totally was. If we're good with this, I'll switch over to that question. But we will be doing this more in 12.3 and 12.4, but I wanted to make sure you guys understood what we're doing and why we're doing it. Because if you're just learning mathematics and you don't understand why, first off, you don't want to do it because it seems purposeless, and no one wants to do something that has no purpose. So there is a purpose to what we're doing, and knowing what it is can motivate you to do that. So let's take a look at what 45 is in 12.2. Let me get that up real quick. Actually, I'm going to do 47 because 45 is your homework. 47 is related to it. 47 takes it a little bit further. 47 is not on your stuff. 47, we start off with y double prime.
Man, you really tricked your students. They thought they would get out of the homework easy.
They don't. The homework is a learning thing. They don't have to turn in homework, so none of them have to do homework. None of you have to do homework.
You get a homework back there? Or homework?
Godspeed if you don't. So this one's like 45, but we have a second derivative. So we have even more to do than 45 has.
Mr. Jones, could you move the whiteboard down a little bit? Sorry.
Yeah, sorry, I had. Oh, sorry.
There
I
you
was
go.
looking. Yeah. I bumped my camera, some bitch.
You say
I don't want
that,
to call
but-
this y. Y is a terrible thing to use right here because our j vector is what we think of as y. So let's call it r. Let's go back to r.
I love R.
And why they use r? R is for radius. So if I wanted to find R prime, we integrate this. I don't have any limits of integration, but what I'm working with is I've got a 1 there and I've got e to the t there, dt. So if I integrate that, my R prime of t is t and e to the t. And since I didn't have limits of integration, I have a constant. And that constant, since R prime is a vector, this is a vector. So where can I go from here? Well, I was given some conditions. This is a condition on the first derivative. R prime is 0. If I plug in t equals 0, I should get just the j hat. I should get 0, 1. But my right side, when I plug in 0, is conveniently 0, 1. So if I solve for c, c is the 0 vector here, and it does nothing. So really my R prime of t is just t e to the t. I'll go back and edit these values in a second. We'll change our initial conditions and see how that changes this. Make sure everyone's on the same page. Now, if I want to integrate again, I could get my position vector, right? Again, we have another constant vector. I'll call this C2. We'll call this C1 up here. This is my R of t. And again, I have conditions up here. I've got R of 0 equals 2i. So if I plug in 0 for t, I should get 2, 0. But what I have is 1/2 1 plus C2. So I can find C2 by solving for it, subtract the vector on the right from both sides. Oops. And I get C2 equals, not C squared, C2 equals 2 minus 1/2 is 3/2, and 0 minus 1 is -1. That's my C2. And so my actual answer, the position vector is R of t equals 1/2 t squared, comma et, e to the t plus 3/2, comma -1. Or I could put this as one vector, 1/2 t squared plus 3/2, e to the t minus 1.
Okay, so we have a question.
So plug in 0, you 1/2 is great, 1/2 is 0.
For which one?
You're right. I totally fucked that up.
Oh, I thought I was doing, I just assumed I was wrong.
Why would you think that you're wrong when it's clear that plugging in 0 would make it 0? That was me being a scrub. That's what happened to a couple people on the test too.
I too love -0. It's my favorite number.
Mistakes happen. Even the almighty Professor Jones. Even the almighty Professor Blakely makes mistakes. And if
What does that
Professor
mean?
Blakely makes mistakes, and he does, Professor Blakely makes mistakes, and he's been teaching James math all the time by the rumor everyone has. James has learned everything from his dad. That means James has learned a shitload of mistakes. So he may not be the most trusted source of information here.
You know, that just leaves the question, where does that leave Mr. Reddit here?
Oh, Mr. Redden's a walking mistake. Okay, so this is how we would do it. 45, you have just one less 7. You didn't have to do it twice. I'm going to go back. Is everyone okay with what we did here?
Got a question?
Yeah, then you get 2 zeros, where it's R0 equals the vector T0.
Very beginning.
Oh, you mean where you got the condition? Yeah, the condition was given.
Is up here.
I'll go. I think we're good.
Okay,
So,
let's change those conditions. So we had 2I and J. I'm going to change them. Let's make it, I don't know, 3, 1 and 1, 2. I'm just totally making shit up. This might go bad. So what that does, I'm going to rewind all the way back to R prime of T when we first calculated it, because it's going to change everything from there on.
It's a lot of whiteout.
So if I go back here, this it doesn't change this first step. We still integrate the same. We still get here, but then R prime is 0. When we evaluate there, we're plugging in zeros. It should equal 1, 2. But what it really equals right now is T evaluated at 0 is 0, not 1, like I tried to do earlier, plus this C1 vector. Which means C1 is, let's subtract this from both sides. C1 is 1, 1. Right?
If you don't have those initial conditions, you cannot technically find C. Are there other methods in the future to finding C if you don't have initial conditions?
No,
Forget. No.
because when you integrate something and you don't have that initial thing, like in regular calculus without the vectors, when you integrate something but you don't have limits of integration, you're generating a family of curves and you don't know which one you're on, and the initial condition goes, nope, we found it, it's this one right here. So the initial condition selects out which one of the family of curves you have. So we kind of need it to go forward.
Well, that can happen on a 3D plane too, so it'd be like there'd just be a bunch of curves infinitely in every direction.
That's not helpful though.
Yeah.
You don't want a bunch of infinite curves. We generally want one. For real life applications,
What I don't get is how is R prime of 0 both 1, 2, and 0, 1? Is that initial condition we're getting like not on that equation or that vector, or like how is it?
The idea is that we're solving for C. And R prime of 0.
I mean, algebraically, I get that. We can do that. But how is it? I don't know. Maybe like stupid question. Like, how is it equal to both of those vector values at the same time?
Because it's also because while it is equal to R prime of 0 is equal to 1, 2, but it's also equal to 0, 1 plus the C vector.
Right, I'm plugging in 0 right here. So this becomes 0. T equals 0, which means this is 0, and this is e to the 1. Or e to the 0, sorry, e to the 0. That's how we're doing it. So when I plug in t equals 0, I get this, but it tells me I should get 1, 2.
No. I get that. I'm just, so what does initial condition really like mean? Is that like, what do we imagine? Like
It's just something.
a starting point and then an end point? Is that what initial condition means?
Initial
Or like,
means
what-
start. It's a way, it's a condition on that we have that gives us an extra piece of information to solve for C. You will do this a lot in differential equations. It's not that hard. It's just you're new to it. It's not a hard thing. You're plugging in the initial condition. Here it says 0. It could have easily said 1. It could be R prime of, pi. And
No,
in here,
it's
this case, it
not
was
hard
R
to,
prime of
like,
0.
That's not the problem. I mean, I'm just like conceptually like,
So he's not actually, he's not asking mathematically, but conceptually.
like what's. Anyway,
Bad way.
The initial condition is what you would get when you plug in that value. What is happening? We got our R vector at t equals 0. What is the R prime vector?
Or essentially
just
picking from like a whole bunch of different curves, and we're picking just one. That's what an initial condition means.
Yeah, because without that initial condition, I could be that curve, I could be that curve, I could be that curve. I don't know which curve I've got. Picking t equals 0 tells me where I'm at. It tells me I'm on that curve right there. So we don't need these other curves. But it's still, this is R prime a vector. The R prime is the velocity vector. That hasn't changed. So this is the velocity vector at t equals 0. Does that make sense? That answers conceptually what's going on. Okay. So we've got our C1. What we would do at this point is we'd go back, plug it in, and rewrite R prime with that information. And we could integrate it like this, or we can combine it. We can do t plus 1, e to the t plus 1. The results will be the same. So let's integrate that bad boy. I'm going to change that to just regular R. This will be the integral with dt. So if I integrate that, I've got R of t equals 1/2 t squared plus t, e to the t plus t, plus some constant vector C2. Again, we don't know what these family of curves are, so we're finding them. Because finding that velocity vector, how else do I put this? You need to go all the way back to the beginning for it to be useful in a context. So this is the beginning. The position vector is what I mean. You got to get all the way back to the position vector for it to have meaning. You generally don't stop at one derivative. You get all the way back to R. So again, I have initial conditions here. These were 3, 1. So if I plug in 0, R prime is 0, or not R prime, R of 0, this becomes 0. This is 1 plus C2, but it also equals 3 comma 1.
Is it technically illegal? Is this legal?
Yeah, I can see that.
I don't know, that's what I was thinking, I mean, when you add those two vectors, and we're like.
It kind of felt like it was important that it went off.
I mean,
We
you
could have
like-
integrated it separately right here. I could have integrated like this.
Does that mean if you have this, you can break it apart, you can do the reverse and then integrate that way?
Yeah, you can do that. It would still be the same thing.
So, I mean, that looks, I feel like that looks, those two are look a lot easier than that.
Is it the?
Yeah. It's the
And
same.
again,
Yeah, it's just, I mean, it's just.
It's the same with multiplication.
It's kind of the same way that, like, when you have like two different things.
It's 9 o'clock, so I know you guys gotta go. So if anyone's got
I'll be holding
questions, you
my
want to stick
iPad.
around.
I'll be holding my SI hours the usual time from 12 to 2.
See you, Mr. Jones.
See ya.
Hey, Mr. Jones.
Yeah.
I was wondering, where can you find like the recorded lectures at?
Yeah, that's fine. It's the same way that-
They're in Zoom. I'll show. Let me change how I'm sharing real quick.
Yeah.
It's in the same way.
So you go to Tech Connect Zoom,
Mm-hmm.
and when it loads up, I'll show you. You click on cloud recordings, and as soon as this lecture is done, it takes a while to thing, but then I'll switch it to publish. But that's how you'll find it. You can come here and you just click on this and it'll give you the video.
Oh,
Click
okay,
on the
sweet.
files.
Okay, yeah, thank you. Yeah, because I was trying to find it for just for like to like part of my review for the last test, but I couldn't figure it out. So I was like, oh, I'll just go on what I have.
Right.
Sweet. Thank you.
All right. Talk to you guys later.
Talk to you later.
All right.
Thank you.
Laters.
Laters.
Bye.